Greetings, welcome. I haven't posted anything in a while, if anyone noticed, and one reason being that it took a while for parts to arrive for this go at something that's sort of like a window motor, but not entirely like a window motor, although the rotor could be wound as a window motor. And secondly, you can hear in the background the thing printing. I'll show that to you in a moment. That's just the stator. It's a 20-hour print that I don't like it running at night, so I'm hoping it'll be 2 days. It might be 3 days. We're into day 2 now. And then after that, that's just the rotor part. Then you have to print the scaffolding for the coils. So it's still a while. And then did everything go right on the first go? And I'm hoping that if it's not right, it's something that a little bit of sandpaper and a screwdriver will be able to make it okay. But so I'll show you that in a moment. And I also thought, since I have this kind of big gap here, I'll talk a little bit about my thinking about some of these motors, like Faraday's Homopolar motor, the window motor, the zero force motor, the serpentine motor, etc. And I guess just to get the ball rolling here, we'll look at some of this on the internet. If you really back up from it for a while, there are basically two kinds of motors. There's Faraday's version, the homopolar motor, and then there's everything else. And granted, there are lots of subgenuses and everything else. There's like the Tesla AC motor, there's a physically commutated DC motor, and so on and so forth. But there's basically two that are much different. And what's the really odd and cool thing about the Faraday motor, which happened before any of the others, the Faraday motor has no commutation. You just put current and it goes. Every other motor, you need a magnetic flux, and you're taking out, here's this magnetic flux, here's that magnetic flux, we're going to get it to spin. I remember reading a little bit about Tesla as he was trying to figure out how to do the AC motor, and when he was in school, his professor said, well, I think you're, very bright, there's no one going to be able to do the motor like he's talking about. And he mentioned that he was walking, like reciting some poetry of ghosts in his head, and he looked up at the sun and he saw the sun spinning, and he suddenly realized how to do the AC motor. So that's where that came from. But it's a more complicated setup than the homopolar motor. And why did the homopolar motor get lost? So let's just talk about them for a bit, and I'll also kind of explain why, to my mind, it's possible that the window motor and the homopolar motor, they might be kind of like kissing cousins. And I've thought of another motor that I'll just mention to you now that might work, and if it does work, I might not show it to you. If it doesn't work, I probably will. If it does work, it's 50-50 whether I'll show it. Not to sound, but it's just, I don't know. But I'll tell you the idea before I have any idea. And as I said, decent chance it might not work, decent chance it might. Let's get into it, and I'll get this video done. How do I stop it? So just real quick, if we look over here, here's the stator. Here's the rotor printing. We're 10.5 hours into it. It says a 20-hour print. I think it might end up like 15 hours or whatever. It's a long print, and hopefully there isn't some critical error. Hopefully it'll work on the first go, or as I said, with just a little bit of modification. I think it'll be fine. But I had to wait for the PLA, I had to wait for the magnets. The magnet wire just came in about a day or two ago. and so on and so forth. So it's taken a while. Once this rotor is printed, you can see the magnets are those rectangles on the outside. Now you could wind the stator like a regular window motor. You go up, over, under, back. And since there's 8 magnets, you'd have 4 of those windings. Or you could just wind a regular coil like that. If you had a rectangular core, you could even put an iron core in, but since these are neodymiums, they're so strong that you're going to do pretty much just as well by narrowing the air gap and having just an air core. I think you'll do just as well. Or, as we talked about, you could do a serpentine coil where you go up and then down and then up and then down all the way around like that. So there's a lot that can be done with this once it's finished. Here, as we showed in the last video and threw together, is one iteration of this where you have, here's your stator, and then this would be here's your rotor, and then the blue will be the stator for a serpentine winding where you go up, down, all the way around like that. But then if you do that, there's no way to ever have a pickup coil because you've entirely covered the magnets. And so you slide this on the top, you put some magnets in there, and then you can have some pickup coils, and this will also serve as the timing wheel. And that same setup would work the exact same if you wanted to take the wire like that, and then over there you could probably use this exact same coil former and just run it around there and back down underneath for those 4 as we just talked about. Or, and this is what I'm going to do first just to see if the thing spins, you can just run a regular coil up there, down there, and then back. It's just an oblong coil. And then you could put those in series or parallel or do what you want. That would be a more conventional setup. So let's talk for a moment about the Faraday homopolar motor. So here's just Wikipedia, and they note that it was the first electric motor to be built by Faraday, and this was the actual experiment where this current going through the air with a magnet would trace a circle around the magnet. And a common demonstration of this motor that you'll see is something like this, where you take a screw that is conductive, you put a neodymium and magnetic, you put a neodymium on the end of that, and that transfers up to there. So now you have your connection to the positive, and the positive goes to there, and then you take the negative and you put it on the outside, the circumference, and away the thing spins, just starts spinning. So it's kind of curious, and there's no commutation or anything, it just goes. So there's sort of a few questions: is why does it do that? And then the question becomes, why did the normal motors spin? So to understand why it spins, we should talk for a moment about Fleming's left-hand rule for motors. Now this all goes back to what Oersted first noticed when he hooked up a magnet, and oh my gosh, the compass needle's changed. And then he disconnects the wires on the magnet when he wasn't, he was demonstrating something else, but he saw, oh my gosh, the compass needle's changing. There's a relationship between magnetism and electricity. And then Ampere figured out all the math around it, which we don't need to go into and which I don't fully understand entirely. I need to read that. But we can see that there's this left-hand rule where if your current is flowing this way, you have 2 orthogonal forces. The magnetic field goes out at one right angle and the force goes out at another right angle to the current flow. So this right angle force is also termed the Lorentz force. So what you see here is you have a current that goes like this, and then you have a right angle force like that, and that's what spins it around. And it's kind of, let me see if I can find a quick 20 seconds of this. So here we have, again, a picture of just one iteration of this where you have the screw going up to the positive there, so the positive's going down to the center of your neodymium. The negative goes here out to the outside, and then if I've got this at the right part of the video, when you connect it, it does that. Away it goes. And there's no commutation involved. It's just spinning. So that's why I kind of said a little while ago, to me there are two groupings of motors. There's this sort, the first kind that Faraday gave us, and the magnetic field is constant. There's no variation in magnetic field, and there's no commutation. You throw the current in and it spins. And then you have the various AC and commutated DC motors where you're taking advantage of a changing magnetic field and putting the timing in to do that correctly. But it gets stranger, because the homopolar motor can also be a generator. And normally we think of, you need a changing magnetic field in order to generate electricity. But the homopolar motor, the homopolar generator rather, doesn't have a changing magnetic field, and yet it churns out electricity. So here we see a picture of a Faraday generator, and so if you have a connection towards the axle and a connection at the periphery, a permanent disc magnet and say a disc of copper on it, then a current flows. And it's a low voltage current, but it can be very high amperage. The MIT scientist Bruce De Palma, who also worked with the PhD Peter Lindemann, did a lot with this stuff. As they also point out here, it's unique that it just churns out DC without any rectifiers or commutators. It's low current, but it can be it's low voltage, but a tremendous current. And they've had some that are more than 1 million amperes. Just to try to be a little bit more clear on that. So that disc is magnetized like this. And so if you have a connection, say instead of a penny there, you have a plate of copper, or even just some copper foil, or I suppose if the thing is actually electrically conductive, you put one of your leads here, one of your leads on the periphery, and spin the thing, and it just starts putting out DC current. But wait, there's more. There's even more. Let's see if they talk about it here. It's called the Faraday paradox. They don't talk about it here, so let's look up the Faraday paradox. And this one's a humdinger. I mean, I have some ideas what is going on until then. So yeah, there's yet another Wikipedia write-up, and there's a lot of highfalutin stuff here, and then we actually get to the paradox, which is, I'm not, they presented, oh yeah, well now it's all understood. I'm not sure it is. So you can think of trying to generate the current from the generator in three ways. The magnet is held stationary, the copper disc is spun, you get a direct current, acts as a generator. The copper disc is held stationary, the magnet is spun, there's no current, and here's the humdinger. The disc and the magnet are spun together, so if you glued the copper foil to the magnet, now you do get a current. Why is this paradoxical? Well, I mean, it's pretty obvious why it's paradoxical. And Faraday, I don't think he felt comfortable explaining it. So I think Faraday tried to say, well, he didn't try to say, he said that perhaps the lines of flux of the magnetic field are stationary even when the magnet's rotating. And so they have their own frame of reference. And then they go with modern explanations. I don't fully understand what they're getting at here, but they're saying it's a matter of relativity. It's relativistically correct. So they also seem to be saying, as far as I can tell, the same thing that Faraday said, is that it's different frames of reference. And De Palma spoke of spinning objects as creating their own inertial frames of reference. So that's perhaps another kind of framework to try to get at it. But it's an odd one, huh? You know, if the disk and magnet are spun together, you get a current. But if the copper disk is stationary and the magnet's spun, there's no current. But if the magnet's spinning, or the magnet's held stationary and the copper's spun, then you get a current. So much different than the sort of motors and generators that you see in common usage. All right, should we go on? I mean, I got like 10 more hours to print, so why don't we go on? So here's an electromagnet, huh? And you got your current wire, you got your core, and now you have a north pole and a south pole. And that's kind of different than when you just have a straight line of wire. So just to go back real quick to the homopolar motor, here you have a straight line of wire, and that's all you have. So it's got its magnetic field going around on the outside, but there's not really a north or south to it. It's just a line of wire, and it drives the coil this way. Now here, with this cylindrical setup, now you have a polarity with the north pole and a south pole for the electromagnet. And I think the reason it spins is really twofold. One is, you know, if you have a permanent, say, south on a rotor, it'll come in attracted to the north, and then you do the commutation part and shut it off. And now it can spin freely around until the next magnet comes in. But there's also then a second reason, is that you still have the Lorentz force going on. So in other words, you have this part of the coil has a wire with current flowing perpendicular to a magnetic field that's coming in, and so it's driving it by the Lorentz force as well. I think this sort of polarity predominates in general, but you still have that other part. So now that brings us to the window motor. And if we're going to talk about the window motor, we got to talk about Joseph Newman's energy machine. And just putting Joseph Newman motor in there, we see the first result, Joseph Newman's proven 100% working perpetual motion, and then the New York Times voodoo science. So who doesn't trust the New York Times? And I don't see this might be a decent picture of it, might not be, but the window motor is essentially, it is Joseph Newman's motor, and Bedini just did the electrical commutation and made it smaller. But Newman, who we see pictured there, had a 2-ton version of it that he called the Big Eureka. So let's see now with the window motor if we can get an idea of how the thing is put together, and I've already kind of explained to you how it's wired. To also be fair to John Bedini and Ron Cole, it's quite likely they came up with this independently. Neither are here to defend themselves, so I'm not just saying that they copied and improved upon Joseph Newman's machine, but the two are the same idea. And you can see with the rotor that we're printing that this would be one way to wire it. So you have a magnet here, north out, and then south out, and then north out. So north and then south on the other end. So the one hitting here is north, the one hitting there is south. So now you have your current flowing through here. The Lorentz force, the force that Ampere documented, is at a right angle. Let's say it's going to push it this way. You reverse it, it'll push it the other way. So it'll push it that way. Now, this is going here and then up and around. Now it's going the opposite direction. So if you had this one being north and then that one being north, they would be in opposition to each other. This would want to push the rotor this way, this would want to push it, you know, one clockwise, one counterclockwise. And here we just see a cross-sectional representation of that. There's your coil of wire there and there. So these are your magnets. So this one would be north out and this one would be south out. And if the current is flowing out of the screen for this one, it's flowing into the screen for this one, and vice versa. And just as a quick aside, what does that say there? Wait, why would you want to do that? We've discussed that before in previous videos. Okay, so here's the thing. This is now running inside of the electromagnet. It's in the window inside the electromagnet with both the Newman and the window motor. So the north and the south polarity that are created here, I don't think they have any effect on the rotation. The rotation is entirely from the Lorentz force. And so that's why I'm saying the thing is like a kissing cousin to the homopolar motor. Now, one more motor, and then I'll tell you an idea, which, as I said, I don't know if it will work, but one more motor, and then we'll wrap up the video. I apologize, I'm having trouble finding some good diagrams or videos after 2 minutes of searching. But here is an example of a window motor. And what is this really? It's a squat, it's of a zero force motor. It's a squat window motor. So instead of taking the wire up and over like that, you have the wire going perpendicular and then you wrap it around. This whole half of the coil isn't doing anything. And then you wind another one there. So much easier to wind, but you're wasting a lot of the wire. However, what I've seen more commonly, if I can find a good example of it, you can kind of see it there, is John would take a big magnet. This isn't one of his machines. I'd have to look. I'm sure there's still stuff out there. And the magnet would go all the way around to there, a gap all the way around to there, and you'd have these semicircular ones now. So instead of extending the rotor upwards like you get with the window motor, he was making the magnet wider and just having two really wide magnets and then wrapping the coil around in a perpendicular fashion to get the Lorentz force. So we know now that you can have motors that are commutated or that don't need commutation, and we can have motors that are driving off of the asymmetry, the north and the south of an electromagnet, or as in this case, driving primarily off of the Lorentz force, the right angle Lorentz force, from going back to Ampere's work. And we can see that you could have a magnet all the way like that and one all the way like that. And so the question that I've had, and I'll tell you what I've done on this and then what I'm going to do next, this is where it gets out to the goofy thing as we're waiting for the 3D print. Why do you have to commutate this? Why can't you just have north all the way around? A real monopole. And why wouldn't it spin? So what I did, I threw together this while I was waiting for parts. And so now we fit as many magnets on here as we could. It would be nice if they were even closer, but this was about as close as I could get them. And so you put them all facing the same way, say all facing north out of the screen there. Now, if you have too much of a gap, and there's a little bit of this going on, then you don't have flux linkage between the magnets. And what happens is the south that's going into the ground there squeezes out and goes between the two, and so that'll never work. But these were close enough that, you know, it was weaker between there, but they were kind of linked. So now I took an electromagnet like this, and you know the winds are going around and around and around like that. So if you put this thing under here, then that's now at right angles. That's now at right angles. So that's the Lorentz force, and I've shown this spinning. And what was interesting was if I left a gap here and a gap there, it would want to spin and then it would stop at the gap. So all north here and then all north there. It would spin and then it would hit a, I forget what you call that, but you know, a hitching point there, or whatever the hell it's called. And even if you put them all the way around like that, it would make a rotation all the way around to there, and then boom, it stops. And so the question is, why is it doing that if it's all Lorentz force? Why is it? And then, you know, if I put all of the magnets in, it wouldn't budge. Didn't matter how much current I threw into it. It sat there like there was nothing. So again, when you have the magnet set up like this at right angles, that's the, you know, the Lorentz force going on, like with the window motor, the zero force motor. However, it was not a motor like the homopolar motor where you didn't need commutation, and I'm just trying to figure out why. And the reason, I think, is because there's still this polarity going on with the north and a south created, and that force will overwhelm the Lorentz force when it gets to, say, a spot there. Now, the way the zero force worked, if I can show that, well, let's skip illustrating the zero force just for brevity's sake. The question I have is, if instead of this for your magnet, you have this, and now you wind it all the way around, now there's no longer any polarity, right? The magnetic field is entirely confined. However, you still have, and you wouldn't want it circular like that, you'd want it like this, so that each of these wires is straight right angle against the magnet. And so now would it spin in the same way as a homopolar motor? I don't know, but I do give it 50-50. Alright, so I guess that's a lengthy apology that it's taken me a while to get anything spinning for you, but got some stuff printing, and this is all on the back burner. If that thing just spins like crazy, I'm not sure I'd even want to show it, because that would be really cool. But, you know, at least 50-50, it's going to be there and not do a darn thing. But I'm not going to have something like that. We'll go back to, where is it? I don't know, maybe something like this, and that'll give you your answer. You know, if we go back, you can see that it's all north, and so you don't have to worry about 3D printing something. And I don't know what it would do. No idea. Could you imagine if it ran, you know, like those demonstrations of the homopolar motor? You just put some current in and it starts spinning. So I don't know. It's still a ways away. But now I got to work on that. I had too much time to think while I was waiting for stuff. But we'll get something spinning here pretty soon. So thanks for coming along, and remember to keep smiling. Talk to you again later. Bye bye.